Hello, and in this C++ tutorial, we're going to be understanding code and how our computers interpret all the things we type. So first things first is that computers were originally used to perform math functions. It started with addition and subtraction, later on moved to multiplication, division, and then they added modulus, and then it just went like exponents, and it just ended up being crazy. So our computer processors are very good at doing just math operations. So there you go. That's what computers were used for, and it's fundamentally the same thing now, except we've added more instructions and we've made the computers faster, added more RAM, accessible, increased the cache size, but nothing really changed. We're still dealing with math functions. Now, most computers use the x86 instruction set, although nowadays most computers have the 64-bit implementation also, so that looks like x86_64 was developed by AMD. And so in case you're wondering what 64 versus 32-bit is, think of a highway with 32 lanes. Would you rather have 32 lanes or 64 lanes? So more data could be pushed to the CPU and sent to and from RAM from the processor. Now, our computer processor only knows how to manipulate and interpret data, which is technically just math. It's ones and zeros. So how can we browse the internet then? Well, that's partially responsible to our operating system, and we'll get more into that later once the slide comes up. So I talked about binary. I mentioned it in the earlier slides. So all computers use binary to execute instructions. 1 is on or true, a 0 is off or false. Now, computer processors don't take zeros off. They usually have 1 means high voltage, 0 means a lower voltage. The only time that it's truly off is when you unplug it. Also, computer processors work by using transistors. Those are things pictured right here, except these are more general purpose heavy duty transistors that you see in, like, if you were to open up like your stereo or something else like a power converter for like your cell phone to provide the USB 5 volt, you'd probably see this in there. Except computer processors have these in them at like, what is it, 28, 22 nanometers. So, and they basically work like this. There's a base, there's a collector. So I might do a future episode on this that might be separate to programming. It might be part of a computer science slash physics and engineering portion if I do decide to make those tutorials. So basically what happens is current goes in. If it's low current, it's 0. If it's high current, it becomes a 1. Now there's billions of these in computer processors, and those work together to execute the instructions that are sent to the CPU. So how does binary work? Well, first of all, we have to talk about the base 10, which is what we learn to count and how we count today. It's also called decimal, so the reason is because there's a decimal. Haha. Also, dec means 10. So what happens is we have the ones, the tens, the hundreds, the thousand. Now each of these are multiples of 10. Again, why it's base 10. So the ones place is 10 to the first power, to the 0 power, excuse me. The tens place is 10 to the first power, so 10 to the 0. Anything to the 0 power is 1. Then 10 to the first is 10. 10 to the second is 100. And 10 to the third power, or 10 cubed, is 1000. But in binary, we use base 2, where we multiply by 2. Now, multiplication is the same as exponents in that you're multiplying by itself. And that's the only case where it will be true. So everything here, we're multiplying it by itself. So 2 to the 0 is going to be 1. There you go. Now, so this is your ones place. Then next is going to be 2 to the first, or 2 times 1, which is going to be your twos place. So you're just follow along. And then once you get to your third area right here, so 1, 2, 3, this is 2 squared, so 2 to the 2nd power, which is 4. So that's your fours place. and then you're going to multiply 4 times 2, which is 2 cubed, is your 8th place, and then so on. So like 2 to the 4th power is 16, 2 to the 5th is 32. Now, these represent numbers when we can convert between binary and base 10 or decimal. So let's actually try it right now. So what we just covered in the earlier slide was that this is the 1's place, this is the 2's place, this is the 4's place, and this is the 8th place. So if you know that 1 means true and 0 means false, so we know that there's no 1's, it's true that we have a 2, so we have 2. It's false that we do not have a 4, and it's true that we have an 8. Now we can add these together and we'll get 8 plus 2. So let's do something a little bit more complicated. Now I have this math problem right here, so let's do true, there's something in the 1's place, true, there's something in the 4's place, true, there's something in the 8th place, so we can add all of that together. Next, notice I put spaces in between here. Syntax is important with binary. You'll never see it smushed together. There's always spaces in between just because they have to be in couplets of 4, if that makes sense. I think so you'll always see them in groups of 4s. And leading zeros, if so, for example, this number right here was just 10, it would actually, we would put a 0, 0 in front just to keep it a group of 4. It has no difference, it's just there for making it essentially look nicer and easier to read while keeping the proper spacing. And that's important for converting to hex, which we'll get to in a later slide. So where were we? Right, 1 plus 4 plus 8. It is false that we do not have a 16. It is true that we have a 32. So go ahead and add 32 plus that. And so 32, 64, 128, 256, 512. So it's true that we have a 512. It's false that we have a 1024. And it's true that we have a 2048. So if we add all of these numbers right here together, we get 2605 in decimal notation. So this is converting from binary to decimal. And only works, this works for numbers. So let's prove this, that this actually works. Go ahead and open your calculator, click View, Programmer, and let's type in hex. So let's type in 1010. Oops, no. Hex is something else. I said we'd get to that earlier. So go ahead and set it to binary. That's been my bad. So we're going to do 101000101101. Now if you look, make sure this is the same 1010, 0010, 1101. So that number right there, see the three groups equal these 3 groups up here. So then we'll go ahead and select dec, which means decimal, and we get 2605, which is exactly what we got here. So you can see where this is going to be useful. So we're going to go ahead and click next, and binary follows a pattern, just so you know. This is 0, 1. Now once you get to the 2's place, there's only going to be 2 sets, or 1 set of binary numbers that have 2 true values or on values in that decimal place. So that means that once we actually go from 1 to 2, there's going to only be 2 numbers that have that true. Once we go to 2 to 4, there's going to be 4 numbers. As you can see, the trues are right here. And so on for 8. Now this only goes up to what, 6? 1, 2, 3, 4, 5, 6. Yep, 6. So start at 0 and I worked my way all the way up to 13. That's just 8 plus 4 is 12 plus 1 is 13. So this is just the way computers work at a very essential level. Now we'll do hexadecimal. So hexadecimal is basically from numerical values from 0 to 9. Notice there are actually 10 values there, because 1 through 9 is 9 plus 0 is 10. Now programmers needed a way to represent 10, 11, 12, 13, 14, and 15, so basically 2-digit numbers, using 1 character. Now you couldn't do that because if it was 10, you'd have 2 digits, so we ended up using the first 6 letters of the alphabet, and notice that they're capitalized. So that's important also. So as you probably guessed, hexadecimal can also be abbreviated just hex, and I'll refer to it as hex. So hex counts by 16s. So let's see, 16 to the 0 power is 1, or anything to the 0 power is 1. 16 to the first power is 16, and we get 16 squared is 256, 16 cubed is 4096, and then we get 16 to the fourth power, which is starting to get ridiculously big, 65,536. Now, the reason we use hex as programmers is to avoid the complications of binary, because if we have binary and the binary digits sort of go on forever, it's going to be hard. So for numbers, instead, we're going to use hex. So let's actually try converting from binary to hex. Now you can see this is already done, but just follow along. So here we have a true in the 1 and a true in the 2 value. So 1 plus 2 is 3. Now we separate this in columns. So that's also another reason why there's groupings of 4, so we can convert to hex very easily. So we have a 3, so there you go, 3 is 3. Then we group this up as a 2, so we go, there's no 1s, there's 1, 2, because it's true, so we have a 2, which is 2. Now, here we have no 1s, we have a 2, we have no 4s, and we have an 8. So 8 plus 2 is 10. Now remember, A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So essentially what we've done is just taken those numbers that we'd have in decimal, and we just moved them to letters. So we have A23 in hex is equal to 2,595. Now let's actually try this. So go ahead and get your calculator out and go ahead, switch to hex and clear whatever you have. So let's try typing in A23. Notice the binary is 1010, that's right for over there. 0010, that's still the same, and 0011. So yeah, it matches up. And if we go ahead and click dec for decimal, you'll see it's 2595. Now be careful when you're adding or trying to figure out what a binary is in decimal, convert it to hex, because you cannot do this with binary. What I just did, you cannot group. This is actually 101000100011. You cannot split that up and pretend as if, oh, it's 3 plus 2 plus 10. 3 plus 2 plus 10 is 15. It doesn't equal this number. You have to convert a hex and then find your final value. You can also do this by taking 3 times 1, since it's in the 1's value. 3 times 1 is 3. 2 times 16 is 32. And what is this? 10 times 256 is 2,506. Plus 32 plus 1, get this number. So it works. So our computer only understands data. Of course it does. It's only 1s and 0s. So how can our C++ code end up being 1s and 0s? Well, we compile or build our C++ code as .exe if you're on Windows. And basically that is executable, which you could call it a program, essentially. So the operating system is actually responsible for converting the data we compiled into actual understandable binary that the processor will execute and run. So you're probably thinking, well, if everything's data, how can I tell the difference between like a music file, a YouTube video playing, and a text document? Well, we as programmers essentially cannot, but there are ways to find it out, because the operating system, which is OS, manages memory, sort of how when you go to a library, there's an index of books. So it knows where every single book is, in every single row, in every single column, in like whatever level of the building. That's basically what the operating system does. Now everything takes up memory, so the operating system is basically going to be an index and how memory and processing power gets managed for a certain task. Now we will eventually Well, actually, let me explain this a little bit more. Because programmers used to have to be able to declare where in memory something would go. Now, you can see where this is a problem if you wrote two programs, run them at the same time, and they're both taking up the same memory. You can't do that. Think of, again, the library example, you can't have two books in one spot. So the operating system eventually became responsible for managing memory, and programmers no longer had to worry about that. But there are cases where you could declare a memory value or how much memory is needed, and the operating system will find a place in the actual RAM to set it aside. Now, a little bit about computer science. Um, you kind of have to know how code gets executed and how it runs on the processor. So it's sort of like a to-do list. So you get home after work, and let's say you need to walk your dog, go to the bank, buy bread from the store. You can do any of those in any order you want. You could walk your dog first, then go buy bread, and then go to the bank, or you could go to the bank first, walk your dog, buy bread, or buy bread first, then walk your dog, then go to the bank. As you can see, there's a lot of possibilities. Now, if you were to label from top to bottom on your little note sheet 1, 2, 3, that's sort of the order a computer would process the instructions. It goes from top to bottom. Now, this isn't necessarily true, as there's something called an instruction pointer inside our CPU, and that's sort of, think of like having a personal manager finding which is the most efficient way to do something. Now, most of the time, you can specify, oh, do this in order, 1, 2, 3, 4, and it will do it in order. But if you don't specify, it will try to find the most efficient way. Sort of like you can walk your dog, then go to the bank. Let's say you forgot bread, you could go back and get bread. Or let's say you need more bread, your computer can still go back to that task and go out and buy bread. And then multi-threaded CPUs, so like dual core, quad core, and 6-core processors, and even 8-core, technically if you're on AMD, can do multiple tasks simultaneously. Think of having a clone of you, and you have like 4 tasks to do. Each clone could do one task and you'd get done 4 times as fast. Now there's a law of diminishing returns in that the number of core, eventually you'll get to so many cores that it'll make no difference. Mainly because what you've just done is made it more complicated, and it eventually gets so complicated that then you could add an infinite number of cores to your processor and nothing will get done faster. You'll hit a wall essentially. But we can get around those walls by making if you look at processors, they're rated like 2.4 gigahertz. That's the speed. And it's basically the instructions that it could get done, how fast those instructions will get done in the processor. The only way we'll eventually be able, if we do hit that multiprocessor wall, is to increase speed dramatically or switch to a different type of what we have right now in processors is very specific instructions. We'll have to switch to very general instructions. Now x86, I think I talked about it in the next slide. Oops. No, I talked about it earlier, sorry. x86 is very specific, so it can only do those instructions. Eventually we'll move to, most likely, if you know what ARM is, it's like the mobile platform CPUs, but it's also used in servers. It's more general task, and it could do a lot of things that our specific purpose CPUs can't. So it's called RISC processors, I believe. So it's out of order operations, and it just could do a lot of things that specific x86 instructions can't. So eventually we'll have to either add that to our instruction set or just change the way that the transistors in our processor work to compute tasks. Now, the main purposes of this was to know how like the bits and pieces of our computer work, and when we write code, it hopefully makes us write it better because we understand what's happening. Now, think about it for a moment. You can write code, but if you don't know what's happening with the computer or why it's happening, it won't really be beneficial. So the main purpose of this is to kind of get a feeling of how to write better code and understand why we write code. Because the computer can only do what it's told. It's not a smart machine. It's dumb, and it'll only do what you tell it to, so you have to know how to tell it to do something. Now, The reason I brought up binary and hex is that we'll use it later in our programming guides, and it's very important because we'll use ones as trues and zeros as false. So, and we'll also use hex to represent numbers, just because then it's also more efficient, because if the processor can do something without the operating system having to translate it, it's like taking an interpreter out. So the efficiency increases very little, but if you end up writing big code or a lot of programs, um, let's say you write a game, you could use it binary as like a way to manage inventory, where if you have, like, let's say you're holding a knife, right? You could say that that's a 1 because it's in your inventory. Or let's say you have no weapons, so all the weapons are given 0 values except for your fists. So it'll be useful, and I highly recommend that you study it a little bit. And if you're interested, I may make a computer science uh, library or something on YouTube that explains this further. But for programming, that's about all we need to know for now. Now, hope you guys enjoyed this video. It'll definitely help you in the future with programming, and it's essential that you know the basics. And this is the very basics of how computers work. So if you learned something new, please like, subscribe if you like the videos. Leave a comment down below in the comment section if you want to suggest improvements or just anything else that you'd want to know. So let me know what type of videos I'll set out later for you guys. So thanks for watching.